Good afternoon, everyone, and welcome you all to our webinar series. I'm glad to see you again. I'm your host, Surathep from Chulalongkorn University, Thailand. And as usual, our webinar series run almost every Wednesday. Wow. And next week we have another talk next week. And all talks are organized by the Energy Storage Cluster, Chulalongkorn University. Importantly, the events are supported by the Office of National Higher Education, Science, Research and Innovation Policy Council, and the Program Unit for Human Resources and Institutional Development, Research and Innovation. During the session, if you have any questions, please leave them in the chat box so our speaker will address them later. Our program today, we have an interesting talk delivered by Dr. Gopalakrishnan Mohan. Dr. Gopalakrishnan Mohan is a postdoc uh, fellow in the Department of Chemical Engineering, Chulalongkorn University, Thailand. He has several years experience in metal organic framework, covalent organic frameworks, metal silicates, coordination, and materials chemistry. He has worked in research projects across multiple fields. So, well, please, Dr. Gopalakrishnan, I will leave the stage to you. Thank you.
Okay. Thank you, Professor, for your nice introduction. Hi, everyone. Today, I am Gopalakrishnan. Today, I am going to present emerged precursors of metal organic framework-based oxygen electrocatalyst towards a zinc battery application. These are my outline of my presentation. First, the basic energy and the development and the gradual growth of zinc battery, particularly in air cathode, oxygen evolution reaction and oxygen reduction reaction and their mechanism. For metal organic framework and their synthesis method, some literature surveys of MOF in energy application, synergetic effect with example, and in situ characterization techniques, challenges and possible research direction of MOF in energy application. Why the energy is important in present days? All the present days, the COVID-19 pandemic has forced all over the world, and it interrupt our day-to-day life activities as social activities and everything. At present we are all under lockdown. However, energy cannot lock down. During this pandemic, we have used a force of energy over the world. Peoples are connected through People are connected through cell phones, computers, other network devices. So energy is most important than anything. These are the energy sources: wind power, hydropower, and solar. They are renewable energy sources, and these are non-renewable energy sources: oil, coal, and nuclear power. So this is a data collected from International Energy Agency. It's a world data, consumption of energy and generation of energy. So from this data, we have used 64% of fuel traditional. We are used the energy consumption 64% of the traditional fossil fuels and 21% of nuclear power sources. And how we generate the same 61 percentage of we are generate energy through fossil fuel, 35 percentage of nuclear power sources. So however, we use the majority of the energy from fossil fuels. So what happen if continue usage of fossil fuel in future? Just there is a 1 minute video clipping. So you all enjoy the video. So it ever increase the environmental pollutions like global warming, climate change, and most important, we don't have enough fuel resource in the earth. So however, we need to conversion the energy storage technology. We need to convert the energy. So that energy must be clean energy. It must be affordable and easy accessible. Most important, it's a eco-friendly energy. So the continued innovation of new and compact portable electrochemical energy devices are battery, fuel cells, and supercapacitors. These are the modern technologically energy storage devices. This the basic principle is they convert chemical energy into electrical energy through redox process. While oxidation, it gives electrons, while reduction, it consumes the electrons. During this process, it gives energy. Nowadays, lithium-ion batteries are most widely utilizing energy storage devices. It is in the saturated market of electrical and electronic devices and growing market of the industry and transportation. However, it has some disadvantages, like that's poor safety, as well as it have high cost, and if we can operate these devices at optimal temperature. Although the other metal ion batteries are available, sodium ion battery, so it have low energy density. However, lithium sulfide batteries have high energy density but poor stability. In these regards, metal air battery have recent interest in the field of energy storage because due to the high theoretical energy, great availability, and low cost and low level pollutions. Zinc air battery can divided in two types. One is a liquid battery and solid state battery. This is a schematic illustration of liquid zinc ion battery. Here, zinc metal as anode, and it contains a separator and concentrated alkaline solution and air cathode. The electrochemical reaction is zinc react with oxygen molecule, it gives zinc oxide. The backward reaction, zinc oxide converted as a zinc as well as oxygen molecule. During this process, it produces energy. So of course, the cycle life is important in the research and development field. So it depends on anode electrode deposition and shape and morphology of the anode and electrolyte solution. The other side, an air cathode, the two major important reactions limit their efficiency of the battery cycle life. So these are the reactions: oxygen evolution reactions, oxygen reduction reactions. This reaction, hydroxide ion converted as a oxygen molecule during the evaluation reaction. Then reduction reaction, the oxygen molecule again converted as a hydroxide anion. This efficiency will increase. We can we can put some catalyst on it. It can increase the reaction rate of this. So nowadays, peoples are using precious metal catalyst. Palladium carbon and ruthenium oxide and iridium oxides are they are using for this reaction. So the mechanism can divided in two types: two electron pathway and four electron pathway. Due to the hydrogen peroxide, due to the hydrogen peroxide, protection of two electron pathway is not suitable for this mechanism. However, the four electron pathway is most suitable, well suited. So let's see the OER mechanism here. First, the metal reacted with the electrolyte. It converts as a metal hydroxide. During this process, it releases the one electron. Further, the metal hydroxide convert as a metal oxide. The second electron was released. The further, metal oxide released as a metal oxyhydroxide. The third electron was released. However, the fourth electron released during the oxyhydroxide converted as again metal. This is overall the four electrons released from this process, and the OER is a reverse process of the OER. and in this process they consume these 4 electrons. However, here the reactive oxygen species main driving force for these reactions. How to evaluate the OER and ORR reactions? That is, here I am showing 4 methods. First, over potential. Over potential is the most effective method to evaluate the reactions. It refers the gap between the potential and the specific current. If you have a bifunctional catalyst, we can use this equation, delta E equal to Ej minus E12. Here Ej is the onset potential of OER and off-wave potential of ORR. It will give the graphical explanation. If we compare with our catalyst in this graphical explanation, we can get our catalysts are excellent catalysts or poor catalysts. We can compare from this slope. And taper slope method, this is an empirical formula. Eta equal to B into logarithm of J by J naught. Eta represented as a over potential, B is a gradient of total line, J is a current density, and J naught represented as a exchange current density. When eta is low, your catalyst must be effective. Then another method, turnover frequency. In this method, the number of reactions occurred at unit time at unit surface area. It is also mentioned here, there is an empirical formula. It represents as a current density. A is the area of working electrode and F is the Faraday constant and N is the number of mole active site of the material. Also, the stability also important factor of battery life. We can analyze the stability through cyclic voltammetry, chromoamperometric, as well as the three electrode systems. Sorry. And the morphology of the catalyst we can analyze by XRD, SEM, TEM, as well as the binding energy we can analyze by XPS. So, what is the problem when using the precious metal catalyst? Is high cost, low natural reserves, and it is a single reaction catalytic and poor durability. So the research interest focused on alternative catalyst with non-noble metal and low cost. It must be durable, and most important is a bifunctional catalyst and eco-friendly, of course. So MOF is a promising alternate catalyst for this OER and ORR reaction because it is a class of material with porous crystalline structure. How we construct the MOF? MOF we can construct it through metal ions and metal ions are metal clusters connected through the organic ligand to can make them off. This MOF have Taylor composition. We can see the Taylor composition. It is having a large surface area as well as the surface area to explore the active sites, and it accelerates the most electron transport during OIR and ORR reaction. A different synthesis method of MOF. First, microwave synthesis. In this method, we use a microwave radiation. It will take times 4 minutes to 4 hours. Then mechanochemical method. It's like a ball milling method. Here we takes 30 minutes to 2 hours. Like sonochemical method, we use ultrasonic radiation. Then sol- slow evaporation method. This method is a crystal growth method. It will take long time, 7 days to 7 months. And electrochemical method, electrical energy 10 minutes, it can take 10 minutes to 30 minutes. And most favorable method is solvothermal method. We use high temperature synthesis of MOF. It have great stability. It will take 48 hours to 96 hours. MOF in energy application. In early stage, MOF studies only focused on macrocyclic synthesis and crystals. After the development of nanotechnology, MOF received wide applications in the field of gas sensor and gas storage system and organic catalyst. It is gradually grown on in the field of energy application. We can see this. After 2016, it gradually increased in the field of energy application like supercapacitor and battery. So some literature's report of MOF in electrocatalyst. This is a macrocyclic MOF. It can synthesis from triformyl chlorofluosinol, parasoluble sulfonic acid, and different types of amine linker in the presence of uh, polystyrene substances. It produced a macrocyclic COF. They can change the linker. They can get different types of MOF. In this COF, they reacted with copal acetate and they produced macrocyclic MOF. They can evaluate the OER process, OER activity both cough and mouth, but the mouth exhibit higher activity due to the improved porous structure can be easily accessible for the active sites. Similarly, the another interesting morph is a dual linkage morph, a synthesis from hexaminobenzene. It get polymerized with iron and manganese to form well packed structure as well as hierarchical porous. So this is most important. This is a bifunctional catalyst, and it act as a they compared with the efficiency with precious metal catalyst. It is nearly equal that equally the efficiency is equal, and they analyzed battery performance also. It gives a better performance towards a zincer battery. Then another interesting report. This is more hierarchical structures are that structures instability in presence of water and other organic solvent. So to overcome this, the existing mop they prepared with two different synthesis method. First, they synthesis with ultrasonic method. It will give sheet-like morph. Further, they can adapt it with the solvothermal method. It give porous structures. The instability moiety was removed. They will get the porous structures. This porous structure can significantly accelerate the charge transport oxygen evolution reaction. We can see the OAR. The red one is ultrasonically synthesized morph. The the black one is both synthesis method. It have higher performance compared with the ruthenium oxide. The another synthesis method, it's a puffing morph. First, they will prepare with single dimensional zinc and triazole. From this morph, they are puffed with copal and iron metals. Further, the fusion formation of carbon network morph while pyrolysis. This is an energetic morph. However, it have some difficult in the synthesis method. The same research group, they synthesis a three-dimensional morph, then they can publish in the nanoscale paper. And this morph can easily access the active sites during OER and OR process, and it can give the better performance towards a zinc battery. This is carbon nanotube morphs. The first they morph synthesis by cobalt and nickel along with carbon nanotube. Then further they will the surface was coated with dopamine. During the pyrolysis, the reactive active species of cobalt and nickel anchored on the cubic surface. The excess of reactive oxygen species removed by the acid etching. Then this move has an excellent bifunctional activity as well as it a better performance towards a zincer battery. This is another interesting techniques they use to synthesis. They can synthesis the morph directly through the nickel form. During the pyrolysis, the cage structures are formed. It is a self-supported morph. This morph have excellent activity towards OER, and ORR process, ORR catalytic activity, and it gives a better performance for zinc hair battery. The synergetic effect. This is the activity different between two different morph. When two morph mixed with one compound, That compound tune the electronic surface structure of the surface that alter the binding strength of the intermediate. This is feasible. This is favorable for the reaction of ORR and OER. For example, nickel and iron morph well mixed, they can perform the OER activity. It gives better performance compared with our precious precious catalyst. The thing is, the Fe morph alone electrochemically inactive. When it mixed with iron morph, it can give the better activity. It indicates the synergistic effect between nickel and iron of inter and intermolecular interactions. This is another similar examples of synergetic effect, and that two different morph directly grow through with the nickel form, and they evaluate OER performance. It gives a better performance, as well as the iron nanoparticle mixed with endowed graphitic carbon. It gives a better ORR performance, as well as they can give the better durability of the battery testing. Another morph, Gopal and iron morph, they can evaluate for, they can mix it together and they can evaluate for the OER performance. In-situ characterization techniques. It is a modern techniques to continue monitor the reactions and side reactions, and it give the real-time structural information about the ORR and OER reactions, and the morphological changes also we can observe through these techniques. This is the setup of these techniques. It is a similar three electrode system. However, here they can introduce one slit. In this slit, they can process the X-rays and detect. They recoil the X-ray. They can detect the recoil waves. They can give the all reaction information. This is a principle of this techniques. This is a catalytic surface. The surface absorbed by the intermediate reactions, while X-ray passes through this surface and ejected like this. They can detect the process. They can get the all the reaction informations, and we can continue monitor of the reactions. Currently, these techniques are developed. It can available for the Institute X-ray XRD, Institute TEM, Institute XAS, and Institute Moss and Raman spectroscopy. The techniques used, one report is the techniques used, and they publish JAX, and in these techniques they synthesis manganese doped gopal ferrate and to evaluate ORR reactions. During this reaction, manganese and gopal, they can interchange the oxidation state during the redox process. However, the iron remain oxidation state is constant. So they conclude that the manganese and gopals are synergistically active sites to accelerate the ORR reaction, and the Fe stabilize the phenyl structures. Challenges and possible direction of the research. Yes, as we discussed in the previous, MOF have limited in the energy application. We can improve more MOF, and it is difficult to the large laboratory scale to industrial scale, large scale preparation, and the conductivity MOF. Yeah, it's one more difficult because we can introduce some electron rich elements, nitrogen, oxygen, and the other elements we can introduce from the MOF. It can increase the conductivity. Of course, the kinetics parameters of the ORR and OER, and further we can improve the structure stability and tuning the porosity of the MOF, and the in situ catalytic, that modern techniques are not that much explored. So overall, the development of efficient MOF electrocatalysts for the energy application, it's not only for the industrial, and it can applicable for some potential problem also. Our detailed review of a recent oxygen electrocatalyst manuscript just accepted in material chemistry today. I thank Professor Suratip and the research group for his constant support for my new direction of research. Thank you all for your get attention.
Thank you. Thank you very much for your interesting talk. Do we have any questions from the audience? Any questions? Just type in the chat box, or you can, if you want to join the stage, is of course I can invite you. But please text me first that you want to join on the stage. Okay. From your review, you review the application in terms of
Yes,
catalyst, right?
yes,
Catalyst, yeah, oxygen catalyst.
yes,
I think that there's possibility to apply MOF, of course, a covalent organic framework also, COF, I
yes,
mean
yes,
MOF, as a host material. I mean intercalation host material for zinc ion or any multivalent a metal ions.
yes, 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 yes.
Mhm.
We can apply. We can apply. Oh, what is the benefits of the MOF is it have a
Mhm.
metal active center, metal
All
active
right.
center. But in the presence of a cough, there is have electron rich element like nitrogen dope, sulfur dope.
Mm-hmm.
These coughs are very active in the electrocatalyst field.
I see. All right. Yeah. Mm-hmm. Any question from the audience? Well, last time, can you show us the abstract, graphical abstract again? That one, that
Yes, 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 yes,
yeah, slide with graphical abstract. Yeah, this one where
yes,
you separate into three types: coordination polymers, covalent organic polymers, and pyrrole-free polymers.
yes,
All
yes.
right,
I can
and you,
explain.
yeah, and I see another application of cough and MOF. They can be used as a platform. I mean, as a template to for the synthesis of porous carbon structure, something like that. Yeah,
Yes, yes, yes. Gravity
yeah,
carbon nanotubes.
yeah. Similar to what carbon nanotube, right?
Yes,
But we
yes,
start from MOF first, or we start from COF first, and then we calcite it, use high temperature, right? And
yes,
turns
yes,
everything to carbon. Uh-huh. Yeah.
yes, sir. Yes, sir. And also oxygen also is not important for the synthesis because while pyrolysis it get carbon dioxide. It
Mm-hmm.
release it emit the carbon dioxide. So oxygen also it's not stable to synthesis of MOF. Some nitrogen rich compound will be more effective as well as
Mm-hmm.
the electron transport, mass electron transport. It can help because of nitrogen. Sorry, electron rich elements, nitrogen, sulfur.
Mm-hmm. All right. Yeah. Okay. Any more question from the audience?
I think I complete very soon. I can
Mm-hmm.
establish.
Mm-hmm. Okay. All right. Well, can you? Yeah. We have one question from Aswin. Can you see the chat?
Yes,
Can you
yes,
read
yes.
it from the chat? Yeah. Yes, please.
Yeah, yeah,
Read
yeah. I
it
would like
now
to
and
ask
then.
the
Well.
impact of the porosity of MOF with oxygen electrocatalyst. How you improve the structure stability based on your experience. Yes, yes. The porous MOF is well suited for electrocatalyst, as I discussed in the previous slides. Also, uh, the porosity will easily access for the active sites. The active intermediates easily will go through the porous size, and it can stable stable and it can convert. The porosity is more important. How we prepare the porosity means, we can design the MOF first, then we'll go for thermolysis. During the thermolysis, that means pyrolysis. During the pyrolysis, it gives a porous structure. How the porous structure create means, the unstable moiety or unstable metal nanoparticle removed from the porous, so it can morph get have hierarchical porous structures. A short morph, the porous morph will give a better activity towards.
Okay.
How to
Well, do you
improve
satisfy?
means, you can plan, and you can plan the ligands, the linkers. It can get more porous size.
All right. Okay. And well, okay. All right. I hope that the answer satisfying you. All right. If you have more question, of course, you can type in the chat. Or if you want to speak on the stage, just tell me. All right. Well, it's possible to, what's it, to prepare the muff using multiple ligand, also multiple metal center.
Yes, it's possible. Nowadays, the peoples are looking at dimetallic morph and trimetallic morph, along with the
Mm-hmm.
two different linkers. They can
Mm-hmm. Yeah.
introduce amine, yeah, they can introduce amines, as well as they can use for carboxylic acids.
Yes. And I
Yes,
and
definitely it
I
can
think
help.
they can find application in energy storage, right?
Yes, sir, yes.
Mhm. Okay, so wow, thank you very much. If no more question, I'm going to close the webinar today. And well, thank you very much for your talk, interesting talk. And
Thank you, sir.
remember
Thank you.
that we still have another talk next week by, yeah, our guest from South Africa. Mhm. Okay, thank you very much for today. Thank you, everyone. Okay, have a good day. Bye bye.